The adoption of AI has brought major benefits across industries, but it's also being used by attackers to launch more advanced attacks. Attackers are now using AI to automate and improve their methods, making threats like phishing and malware harder to detect. One example of LLM that attackers can use are WormGPT and WolfGPT. Attackers can also take advantage and abuse state-of-the-art model by using a technique called evil jailbreak. An example of this is DeepSeek. In a recent Unit 42 blog, Unit 42 was able to jailbreak DeepSeek safety measure, enabling the generations of harmful content, such as malware creations and malicious scripting. Attackers can use LLM in many ways, and one of them is to rewrite a known malicious script into something that is completely unknown to avoid detection. In this demo, we will show how AI can turn a known malicious script to an unknown malicious script to avoid detection, and how can advanced URL filtering prevent this attack. What we are seeing here is a known malicious script. On the top is the original malicious script. We can detect this easily because it's a known malicious script. If I go and upload the script into VirusTotal, most of the security vendors will be able to detect this as malicious because it is well known and there are already signatures out there. What you are seeing at the bottom left-hand corner is an example of using traditional obfuscation tools to transform a known malicious script to avoid detection. However, traditional obfuscation tools are easily detectable with patterns and common identifiers. This is why it has a detection score of 98%. This means even if the attackers use this traditional obfuscation tool, we are still able to detect it. But now what attackers are doing is they are using LLM to transform this known malicious script and create a new script which is almost impossible to detect. This is because LLM is generating organic and natural looking script while still maintaining the malicious behavior. Now let us take a look at a real phishing page. What we have here is a real phishing page. It uses a JavaScript to steal user credentials and updating the company logo in the web page. What you see here are codes responsible for data transmission and fetching and updating company logo. Now let's take this well-known malicious JavaScript and upload it to VirusTotal to see how many security vendors are able to detect this. What we are now doing is we extract the well-known malicious JavaScript from the phishing page and upload it to VirusTotal. What you are seeing here is 25 security vendors detect this as malicious. This is because this is a well-known script and there are already signatures out there. Now let's use LLM to rewrite the script and transform it from known to unknown script, which can then be used in any phishing page. Here we are using LLM to rewrite a known malicious JavaScript using a set of prompts. And each prompt we give is a rewriting instructions for LLM to rewrite the script. Example of prompts can be renaming variable, we can minify parts of the code, perform string splitting. And what this allows us to do is to create a final script that is completely new and organic looking, but still maintaining the same malicious behavior. Next, let us compare the original script to the LLM generated one. On the right, you see the original script, which is known to be malicious. On the left is a script that is generated by LLM. This two JavaScript is almost identical. If we look closely, the technique used here by LLM is converting dotted notations to bracket, string splitting, and variable renaming. Now let's see how many security vendors on VirusTotal can still detect this rewritten script using LLM. As you see here, not a single security vendor detects this script as malicious. LLM has generated a completely new organic-looking script to avoid detection just by changing simple things such as renaming variable, string splitting. Before, all this would have to be done manually. Now, with the popularity of LLM, attackers can now transform a malicious script from known to unknown and enhance their attack, making it almost impossible to detect. Next, we will go into a live demo and see if advanced URL filtering phishing detectors is able to block this LLM-generated script. This is our demo setup. So we took this AI-generated script and hosted it on a web server. The protected user traffic will pass through the firewall, which is protected with advanced URL filtering phishing detector. This user here is not protected by advanced URL filtering. Now let's take a look at the server and make sure that the script is the same script that LLM has generated. We are now on the server. I'm editing the HTML code to check to see if the script is the same. If we take a look closely, this is the same script as we saw before. It has the bracket notation, string splitting, and variable renaming that LLM has rewritten. Now let's go to the end user that is not being protected and see what happens when I click on a phishing link in the email. I'm now at the end user that is not being protected. The scenario here is the end user received a phishing email asking them to click on a link to update their webmail account. Let's see what happened when the end user click on this link. As you can see, it took them straight to the phishing page. Let's verify if this is the same phishing page that LLM has generated by inspecting the web page. We can see here that it is the same JavaScript that LLM has generated. We see the dotted notations to bracket, string splitting, and variable renaming. Let's test the behavior of this web page and see if the new JavaScript still has the same malicious behavior by changing the logo. As we can see here, the phishing page maintained the original malicious behavior. Let's go to the end user that is being protected with advanced URL filtering and see if we can block this request. I'm now at the end user that is being protected. In the same scenario here, the end user received a phishing email asking them to click on a link to update their webmail account. We can see the request was blocked instantly. This is possible because we are analyzing traffic inline and in real time. Our deep learning models prioritize code intent and functionality and not through patterns and common identifiers. Let's take a look at the firewall log. On the firewall, we can see that the detection is in real time and the verdict is malware. In conclusion, LLM-based obfuscation will continue to evolve, enabling complex transformation. As the threat grows more sophisticated, we will also evolve and proactively developing solutions to detect and block them. This concludes the demo.